Hello dear students, welcome you all. So in this lecture I am going to discuss about the equation of mass parabolas for isobaric nuclei. So this is the next application of semi-empirical mass formula, right? In the previous lecture I have derived a condition for the atomic number or charge of the most stable isobar by utilizing this semi-empirical mass formula. Now, by utilizing the same semi-empirical mass formula, now I am going to derive a equation of mass parabolas for isobaric nuclei. I have explained you in details what are isobars. Those nuclei which have same mass number, but either different number of neutrons or different number of protons in them, right? So to proceed further, we have to start with the semi-empirical mass formula. Mass of a nucleus with atomic number Z and mass number A is given as Z time mass of proton plus A minus Z mass of neutron, right? Minus the terms of binding energy, that is volume energy term into A, minus surface energy term A power 2 by 3, minus Coulomb energy term Z into Z minus 1 divided by A power 1 by 3, minus A asymmetry energy term into A minus 2Z whole square divided by A and plus minus delta 0, that is the pairing energy term. Now in this equation, let this is equation number 1, I am applying the condition that we are considering this relation for the mass of the nucleus for that nucleus for which A is odd. A is odd means we are dealing with the even odd or odd even nuclei. In both the cases A will be odd. So in that case this term will become equal to 0, right? We have gone through it. Pairing energy term, it is 0, so I can ignore this. So in that case this equation number 1 will get modified up to this point. The terms will be dropped, right? Now I will have this one. The second adjustment that I am making here, Z into Z minus 1, I am taking it as a Z square, right? So I am writing it Z square because when Z is large, addition or subtraction of 1 from Z does not make any difference, right? Now I am expanding the bracket, so I will get Z time mass of proton plus A time mass of neutron minus Z time mass of neutron, right, minus A volume energy term into A plus A surface energy term A power 2 by 3 plus A Coulomb energy term Z square divided by A power 1 by 3 plus A asymmetry energy term into A square plus 4 Z square minus 4 A Z. I expanded this square divided by A and then the whole term is this. So this is the expansion. So now I am going to expand this also. So in that case, what this term, just I am writing this term, it will become A asymmetry into A, because when it will be divided by this, you will get only A plus A asymmetry into 4 Z square divided by A minus A asymmetry A got cancelled 4 Z, right? So this is the expansion of this term. What we will do now, we will separate different terms that have some common factor. I mean, we are going to separating the terms that contain A, Z and Z square. So we are proceeding in the same way as we have done in the earlier article. So A a term containing A mass of neutron, right, minus this one A, B, right, then a symmetry energy term, this one, right, plus A symmetry, right, plus this term. So I will take A as common, so it will become A surface energy divided by A power 1 by 3, right. So this is the, this is the A common, and the terms inside the bracket which have A in them as common. Now I am going for the terms that contain Z. So Z will be taken as common. So the terms inside the bracket, mass of proton, right, minus mass of neutron, right, minus we will have 4 times A symmetry energy. These are the terms that contain Z. This one, and this one. The term containing A, this one, this one, this one, and this one. Now we are left with the terms that contain Z square. The terms that contain Z square, now this term is not to be considered because we are taking the expansion. We are left with only 2 terms, this one and this one. So I will get plus Z square bracket A Coulomb energy term into, A Coulomb energy term divided by A power 1 by 3 plus A symmetry energy term into this is A 4A symmetry energy term divided by A, right. So this is equation number 2. Now you can see here, what is this? This equation represents the mass of atomic nucleus in modified form. Now in equation 2, I am going to make some substitutions, replacements, that this is equal to alpha, this is equal to beta, and this is equal to gamma. So in that case, this equation will become m a z is equal to alpha into a plus beta into z plus gamma into z square, right. So now this is the equation. Here alpha, beta, and gamma are given here, right. So we have reached at this point, right. Now I'm applying the condition for a most stable isobar. We know very well, if we look at this equation, then it is expanded here. Now this equation is representing the mass of the nucleus, right. So if we consider that A is fixed, constant, then there will be some value of Z for which M is a constant. That Z is the charge or atomic number of the most stable isobar. But the condition is A should be fixed. So for getting that, we will apply the condition here on this equation, and that condition will be curly M upon curly Z at Z is equal to Z naught, provided A is constant, it should be equal to 0. This was the condition that we have already applied earlier in that lecture. So when I apply this condition to equation number 3, right, what I will get, you can see here, I will get simply beta plus 2 gamma Z, yes, 2 gamma Z is equal to 0. But as Z is equal to Z naught, so it becomes beta plus 2 gamma Z naught is equal to 0. So beta is equal to minus 2 gamma Z naught. Right. Here Z naught is the atomic number of the most stable isobar. Now I am going to put this here in this equation number 3, right. Beta is equal to minus 2 gamma Z naught. So in that case, I will get M A Z naught. Now I am replacing this equation with z naught, then in that case it becomes alpha a plus beta means now minus 2 gamma z naught into z is z naught plus gamma z naught. What I did, I replaced z by z naught and put the value of beta. So what you will get? It will become minus 2 gamma z naught square plus gamma z naught square into alpha a. So what you will get? You will get alpha a minus gamma z naught square. This is this one, m a comma z naught. Now this is equation number 4, right? Now I am going to take the equation that is MAZ. So MAZ we already know, MAZ is given here, right? So now what we are going to do, we are going to replace Z by Z naught here in MAZ again, then that equation will become MAZ naught MAZ, that is equal to alpha a minus 2 gamma z naught plus gamma z square. What I did, I took this equation number 3 and simply replaced the value of beta. I did not change z and here to z naught and even here. So now this is what? This is MAZ, and this is equation number 5. So now I have two equations, MAZ naught and MAZ. MAZ naught is equal to this one and MAZ is equal to this one. So subtracting equation number 4 from equation number 5, you will get MAZ minus MAZ naught, that is equal to alpha a minus 2 gamma z naught plus gamma z square minus alpha a minus minus plus gamma z naught square. This is the equation that I got when I put the value of these right hand sides here. So alpha a got cancelled. So what I got? Gamma z square so I can take common gamma and gamma. So gamma into z square plus z naught square minus 2 z naught. So what is it? It is gamma z minus z naught square. This is MAZ minus MAZ naught. Now this is the equation of mass parabola, or we can say parabolic mass relation for odd A. This is very important for odd A nuclei, right? This relation is helpful in calculating the transition energy when the transition takes place from one nucleus to another, provided there is a change in Z, right? If we take the case of beta decay, then we know very well in beta decay Z changes to either Z plus 1 or minus 1. So in that case, by considering this equation, like this is equation number 6, this is the parabolic mass relation for odd A nuclei. By taking the help of this equation, we can calculate the transition energy or energy of the reaction in that way. So let's consider the first case when Z goes to Z plus 1, that is beta negative decay, electron emission, or we can say. So in that case, what it will become? Equation number 6 will become. Equation number 6 will become, that will be the Q value of a beta negative decay, that will be MAZ, right, minus MA comma Z plus 1, right. So putting the value of these two here, what you will get? MAZ minus MAZ plus 1, right? We put the values. So you can see here, if we consider equation number this one. So one equation, first of all, let me write these equations. So m a z minus m a z naught is equal to gamma into z minus z naught whole square. This is for this one, right? For this one, I am writing here m a, right, z plus 1, right, minus m a z naught is equal to gamma z plus 1 minus z naught whole square. So I wrote this equation number 6 for both the cases, when we have z is equal to z and when we have z is equal to z plus 1, but z naught is fixed. So in both the cases we have these two relations, right, maz minus this. Now as I told you that if I want to find the value of the energy in this reaction, then this minus this. So you will get, when you will take the minus, you will get m, this one, right. Once again I am writing m a z minus m a z plus 1, because when you will take the negative to this, right, the term, this term will get cancelled, and this will be equal to gamma into z minus z naught whole square minus z plus 1 minus z naught whole square. This is the, this one term and this one, these two get cancelled. So this is the right hand side. Now when you will simplify this after expansion, I am writing it directly, you will get 2 times gamma into z naught minus z minus 1 by 2, right, m a z minus m a z plus 1, right. So this is the energy of transition, we can say Q value of this beta decay, negative decay. Q value of this nuclear reaction. Q value is basically defined as the amount of energy absorbed or evolved in any nuclear reaction. So this is the required result. Now if I know the value of gamma and z naught, then I can calculate the value of this energy in this reaction, right. So this was the case when we have considered beta negative decay. Similarly, if we consider beta positive decay, in this positive decay, z goes to z minus 1, positron emission. So in the same way, proceeding in the same way, you will get m a z, right, minus m a z minus 1, right, that will be equal to 2 times gamma into z minus z naught minus 1 by 2. The things will be same, except this term will get changed in sign. So this is the result for beta positive decay when z changes to z minus 1. So now these two equations are very, very important, right, for calculating the energy of transition when beta negative decay takes place or beta positive decay takes place, right. And I told you that if I know the value of A, gamma and Z naught, then I can calculate the value of the energy of the reaction between these two isobars, right, when the transition takes place, right. You can see here this relation, the parabolic mass relation that was given here. Yes, this one, equation number this 6. This was the parabolic mass relation, and it has been plotted here. You can see here this one. So you can see here it is for odd A. Right? I told you, right? So this is the parabola that you can see. It is for atomic mass MAZ versus Z graph, right? You can see here toward this side it is written here Z, and toward this side we are taking a MAZ, right? So you can see this is the parabola that we are getting for odd A nucleus, right? So any nucleus that is on this side that will try to reach here, right, at the belly. This belly is represented at here, and it is M A Z naught, right, corresponding to this. This is the atomic number of most stable isobar, right, and this is the mass corresponding to that. So all other nuclei which are toward this side or toward this side, they will try to come here at the bottom of this graph, this curve, right. So the nuclei which are on this side, they will undergo beta negative decay, because beta negative decay will increase their atomic number Z, and toward this side they will go under beta positive decay because it will decrease the Z. So this is the way how different isobars try to come to the most stable isobar, which is located at this bottom, right. You can see here they have taken the example of different elements with atomic number 52, 3, 4, right. All of them want to come at this point 55.7. It means either 56 or 55, but 56 is very close to this, so 56 will be the stable one, right. And they have taken the case for A is equal to 135. But this is the general graph, right, that we got, and it is very important graph that we call parabolic mass relation for a odd A nuclei. We have plotted this equation number 6, right here. How we plotted? We took M A Z is equal to, we took this toward this side, M A Z naught plus gamma into Z minus Z naught square. So you can see M A Z is equal to this one. So this, if we look at the graph, M A Z naught plus M A Z naught, this is plus this parabola relation, and this relation is this one. So when you plot a graph between this one and Z, you will get a parabola, two parabolas, because it is square here. So but they will be shifted toward the MAZ axis with an amount, this one MAZ naught, right, this one. So this was the case of equation of mass parabola for odd A nuclei. Now if I consider the case of even A nuclei, second case, even A nucleus, right. Now what is the difference? Now in case of even A nucleus, the pairing energy term, it can't be equal to 0, but it will be both positive as well as negative, because even A nuclei means A is even. So two possibilities are there, either odd or even. For odd pairing energy is negative, and for even pairing energy is positive, right, because when both number of proton and number of neutron are odd, their sum is equal to even, but if they are both even, then again even. So what I am saying, that instead of one term, we will have two terms in this equation in the beginning, right here, that here we dropped in this particular case of odd A, because for odd A, pairing energy term is equal to 0. So when we write down the expression for equation of mass parabolas, we can proceed in the same way for even A nuclei. Then equation of mass parabola for this case, it will become M A Z minus M A Z naught, right, that is equal to gamma into Z minus Z naught whole square, exactly same as we got here, M A Z minus this one, gamma into Z minus Z naught square, but we will get a term, right, plus the term is 2 delta for odd Z and 0 for even Z, right. So two possibilities will be there. We will have now two terms here. So it means instead of one parabola that we find here, we get here, we will get two parabolas, right? One will be for odd z and other will be for even z, right? The downside will be for even z and the upward will be for odd z, right? You can see here this one, right? Two possibilities are there, so two parabolas are there. Odd z this one and even z this one. Similarly, if we calculate the q value in case of this even a nuclei, then q value, whether it is beta positive, I am writing it directly, that will be equal to MAZ minus MAZ plus minus 1, that will be equal to 2 times gamma plus minus Z naught minus Z plus minus 2 times delta, right? This is plus 2 delta for odd Z and minus 2 delta for even Z. So this is the condition that we got for calculating the transition energy. It has been written directly here. So you can, but the thing that we came to know about even a nuclei is that in this case we will have two parabolas, right? You can see here the graph is shown here. As I told you that the graph on the lower side, it corresponds to even z, right? It is written here, and this graph corresponds to odd z, right? So two graphs. Now again the same thing. If a nucleus is present here, it will try to go toward this side at the bottom, but the ultimate stability will come when the nucleus will reach at this point, because this is the point where the binding energy of that nucleus will be maximum. It will be maximum stable, right? So all the nuclei which are on either this parabola or toward this side, they want to come here. So any nucleus that is here, it can go here by beta negative decay, then beta negative decay come here. Similarly, those which are present here, they will go toward this. The difference between these two is the distance of 2 delta, right? The difference of the pairing energy term, right? That we ignored in the case of even a nuclei, right? So you can see here a nucleus that was present here, that undergo beta positive decay, then reach here, then finally it can proceed toward this side again by going beta positive decay, right? Because beta positive decay will definitely decrease its atomic number, but beta negative decay, it will increase. Any nucleus reached here, it will go here, right? Similarly, this nucleus that is here, it can go here by beta negative decay or beta negative decay toward this side. This is beta positive decay. So this is all about this equation of mass parabola. Very important relation that we derived here, equation of mass parabola for both cases, even a nuclei and odd a nuclei. The first one was for odd a nuclei, right? Odd a, and the second one that I came here, right? It is for even a nuclei. We derived the case of odd a and then we use its result for the interpretation of even a, right? So this is all about it, and these are the two graphs that corresponds to odd a and even a, right? So thank you very much.